All right, so let's get started. So this is a unique topic compared to a lot of our previous videos, and we're going to start from the top and take this small steps and slowly. So the problem of reaching agreement is analogous to a group of friends trying to decide on where to meet for lunch. And we're all familiar with how this goes down. These friends work together, they're going through a process, they're trying to reach a common consensus on where to eat. So this means they're only going to communicate via text message, on their phone. In this case, we're not doing face to face. There's no phone calls, etc. This is just information being sent from one person to the others. So in this case, Brooke sends a message to both Alice and Bob asking if they want to do hamburgers as a group message. And this is how the data here is sent. And to simplify this, we're just going to say that Alice and Bob, they're just going to agree immediately, just whatever. So they agree. They both give a thumbs up. And now what we have is all three friends, they're working independently of one another in parallel. They're working concurrently via message only. This is all the information they have exchanged with sending a text message, sending their thumbs up. And at this point, all three have communicated to each other, and all three can see that everyone agrees on hamburgers. So at this point, everyone knows that they can stop coordinating, that their process is done. And essentially, we've got this, now that we had this agreement, we know that it was a 100% chance that we show up at Fuddruckers at 12:30, all three of those friends are going to be there, and they've reached the definition of an agreement. And this is the same framework that's used in distributed computer systems. So pulling over just one example here, multiplayer online games, a whole bunch of different people logged into the same game. The same thing is happening. And then this is also the same concept when it comes to these large data centers or different processes that are spread out geographically, multiple locations. And there's lots of benefits to doing this. They can share workload, a bunch of different users come on at a certain time of day, or they can be closer to people, like certain regions, they can be closer to them, faster, better user experience. Or if one of these gets hit by a hurricane or some kind of national disaster, natural disaster, or so on, the other ones can pick up the slack and there's no loss in functionality. So a lot of benefits to distributed computing. And it started inside of the computer architecture itself. And nowadays we have all of these multi-core computers. It just means that there's a distributed architecture. And here in this example, you can see this one does this many operations, this one does this many. So distributed architecture and concurrent multiple processing gets us more speed. So now we're going to go into a little more detailed example. And again, way simplified, but here we have four pieces within the computer architecture inside of this phone. The display here, the keyboard input, this autocorrect, and then this word suggestion. And when I push this in button right here, and it's gonna show up on the display. So I have hardware and software in my phone devoted to displaying the letter that I just pushed. And simultaneously, other hardware and software, they're working in parallel. So if I'm misspelling this word, I'm going to get a red line. Or when I add that extra letter, this word suggestion is going to update. It's going to try to anticipate where I'm going. So from a process point of view, the keyboard software is now sending this information to all of its parallel units in this process. And here, we have all four units must cooperate. And it's a note here that there is intentionally no single unit that's put in charge to oversee this, and that is by design to account for errors. We don't do singularity. That having that kind of totem pole is bad for computer architecture business, because if that leader breaks or has a fault, it's gonna break the whole system. So cooperation is a way more robust way of going through this process. So and now we're going to start getting into the problem of consensus. And it is, there's just some simple things that we want to know or that you can imagine, going wrong. So one being, how does this group know? How does this group know that they all have the right information, that they all received an in, and that how do they arrive at this end state? What does that look like? So we'll zoom into this view, and so based on just this first question, does everyone have this? These are some of the problems that we need to account for. So you can have a message that's doesn't get delivered, it just fails in delivery, or other messages might somehow get changed, like an individual bit gets turned or something, and it changes what the message looks like. And there are many more issues that may happen. And you can see here we've reached this point that we've got someone's got an M, two of them had the right one, and one's got something completely different because it's still sitting on the last letter, which is an A. Did not get the update yet. And so now to some of the common protocols, you can imagine we want to do some kind of acknowledgement when something gets sent. Initially, everyone is tracking A as the last letter that was input, and this unit is now telling everyone to update their last input character to the letter N. So it's going to broadcast this out, and it's going to expect some kind of acknowledgement. So here, this one gets the bit change, and it's going to respond with the wrong character. This one gets the right character, but it's not going to reply because it crashes. And this one does not reply because it's broken and never got the. And I'm sorry. And this one is fine, but I never got the message in the first place, so it's not going to reply. And all of these are rare events, but when you're doing billions of operations a second, you're going to run into these. You're going to encounter them. Then another common action, another common protocol is each unit reaches out on a routine basis, a heartbeat, and it's going to check other units, say, hey, do you have any updates? And here comes this other problem is, it's the literal process of updating their value from A to M. This is a very, very small amount of time when you have electrons moving in just one situation to change this unit, but it still requires time, and there is a chance that someone could do a check during that small amount of time, and when that happens, we have no idea what's going to come out of that. It could be the prior, could be the current one, so that's an error as well. And then lastly, they'll say this piece of hardware crashes. There's no telling what might go wrong at this point. And this is when hardware crashes, it becomes an unknown box of problems. And we're going to talk more about this. And so just as an example here, it can arbitrarily just insert something completely false. So, this image here is starting to give you an idea of just how pernicious and challenging this problem is, and just this, trivially small example. And now to the problem of timing. Protocols. Now to get into some of the protocols. So in the early days of distributed computing, grasping with these problems, we started to have certain protocols that were being developed. These are just some example pictures, how to retransmit if you don't hear back, or logging and storing. This one, you can start to see there's more, some more advanced logic going on, more complex types of protocols. But I guess the big takeaway is, this is the protocol as well, is it all boils down to logic. This is nothing but just if-then statements. It's just different organized approaches based on what may or may not happen to make sure the computer does what it needs to do. And there are also hundreds, countless textbooks devoted to this idea. Just an enormous amount of academic content on really just algorithms on this logic. So now we'll get to timing. And there's two ways we're going to look at timing, and we're familiar here with our universal or global clock. Yet as we get into very large systems, including the peer-to-peer like Bitcoin, it's a far better option. You actually use a sequence of events, an order of events, and you just know your location in this sequence. And we'll see more on this in a minute. Right now we're going to stay with synchronous, which works in small distributions, local distributions, like our smartphone example. So here the components are spread unevenly across the hardware board, which means that the pathways between them where they communicate have varying lengths of time and variance and so on. And again, it's an artificial example, but you will have different times, different rates of failure, different variance, and so on between all these individual pathways. So timing becomes timing we don't take for granted. So now back to our process look, and the timing in this piece is, it's not as simple as a clock and a wall that we're all just looking at, but we do have more options based on having a local time. And the first one is just called a heartbeat. And everyone's just going to, at a certain time, everyone just checks the status of everybody else. Just make sure we don't have any changes. Or if we are sending messages to everyone, now we have a sense of what we know their different response times ought to be. It can help us with our logic to increase or decrease message traffic and so on. And then we also have these ways for these different units to stay in sync. So this one is drifting a little bit. Got these little methods to keep them all nice and tight and locked in together. And we still have these protocols to address issues that we know might occur. And in addition to that, good designs are going to have safety nets or backups. So this is known as failing gracefully. So here the autocorrect suspects someone else is failing in the process, and it's just something I made up. So it's just going to revert to something more simple, doesn't need any help from the distributed system, which is more resilient. So in this case, it just stops autocorrecting. Then when that error goes away, it'll replace itself. It's called failing gracefully. There's a lot of balance to that also, because let's say you want to prevent this. Well, you might need to resend messages many more times. And then when you're talking from the whole architecture point of view, you could be talking billions and billions more operations for different errors throughout your phone. That could drain the battery, that can make things slower. So it's all kind of one big balance on what you want for the user experience. A lot of thought goes into these. So now we're gonna get to the Byzantine problem. Spelled that wrong. And we're going to expand the example that we're on, and now we're looking at an aircraft. This aircraft has 4 units, 4 sensors, and they're going to be detecting the aircraft altitude. So, and again, this is still a closed system. This is not a peer-to-peer network. And we'll bring back this piece, and we want everyone to be here at this definition. And arbitrary example again, when the plane changes altitude, we want every unit to have the same value that the plane is at, the correct value. They all need to have the correct value to be in agreement, and they all need to know that they've arrived at the correct value. And so they reach a discrete point where they know that they can stop, and they have successful agreement, and they can move on to the next task they have to do. So Byzantine is it's an umbrella term that defines. It's an umbrella term that is basically saying any type of failure. So there's an infinite amount of ways that something could fail. In this case, sometimes it also refers to bad actor. We'll get more into that in the peer-to-peer networks. And again, the chances of a Byzantine are small, but when you're doing lots of operations, they happen. So in this case, you've got one unit that fails. And now it has all these unpredictable actions. Here it just sends gibberish, which is not bad. It's not in the right data format, so it's a little bit easier to detect. Here it sends the completely wrong information, but it sends it in the right data format, and then it just fails to send on this one. So it can do any type of bad behavior or erroneous behavior. That's what Byzantine is talking about. And so now we get into a common type of protocol that to counter this, we take all of these units through multiple logic iterations, towards finding the agreement. And each one of these steps, they're talking to all the other. So in each one of these rounds or steps, each unit is talking to every other unit. So that's a lot of messages being exchanged. And as you increase the number of units, the number of messages that are going to be sent and received, they grow exponentially. And that makes this consensus problem essentially impossible to overcome. Well, many years ago, this was impossible to overcome. And it's not a small problem. So you can trace this back to the 1970s. Engineers trying to wrap their head around the problem is anything at all can go wrong. How do I reach consensus? So okay, so now we're going to asynchronous, and so instead of clocks, which are not going to be reliable, there's no synchronized time between a larger distributed system. Locally they can use time between components, but between these devices, there's too many challenges. So just first example is they won't be able to synchronize time amongst each other, and then now to the common protocol that addresses asynchronous is just the practice of using counters for each round. So each unit here is going to maintain its own string of counts as it sends messages back and forth. And so now back to our mock example, this unit failure here is going to cause some initial confusion. It's going to go through their algorithm and say here it takes 7 rounds, just an example. And we're going to end with a successful agreement, and that's the new count, 7. So the takeaway for Byzantine now is that in these somewhat larger systems, but still closed, finding consensus is just a nasty problem. And now let's look at a little bit more on why this is hard. We need to get more involved in our example here. So we're gonna take this plane from 20,000 feet. It's gonna drop down 10 feet. We need all the sensors to go through their process and then finish here in agreement, and the correct agreement, knowing that they can conclude the round. So again, we're gonna have a Byzantine failure in this unit, but these three do get the correct value. They do sense the correct value. So in the prior examples, it was oversimplified. Each unit is actually storing the other values sent from the other units. And as a baseline, we don't know what unit it comes from. We just know that it's inbound traffic. And in this case, we have this Byzantine failure, which gives us this different result amongst different units. And again, it's a Byzantine failure. It can send different stuff to different units. And now we have the problem is we can't reach agreement until we identify what unit has malfunctioned and is sending this wrong value. They have to identify this unit so to be able to say this one failed, the rest of us didn't. We know the correct value. We know the Byzantine unit, and we know that the rest of us have the correct value, so now we can stop. Now we meet this definition. So I'm glossing over a number of technical details here, but these nodes basically go through a process where they're going to cross-examine the data from each other by sending messages back and forth in various ways, and they're going to do that and isolate, identify this bad node. The process to do this takes the same number of steps as there are nodes. So in this case, it would take four steps. And then that's why Byzantine is so difficult. So to meet this definition, you're sending a ton of messages. We have 4 units. This is 4 squared in 1 step. So if you do the number of units, you're going to get 4 cubed, which is 64, which seems small, but you go, a typical system, you're going to have many, many, many units. And in this example, 4,000 cubed is it's a big number. So now we go back to the start of our example, and this time we're going to use digital signatures, which lets us know essentially right away what unit is failing. Here they all, each unit signs the data that they send, and we know we can identify bad data. And again, we're going to glance over many technical details, but the short of it is you only need like a maximum of 5 steps to overcome a Byzantine unit when you have digital signatures. So the process is much shorter. So the benefit of digital signatures, the number of messages sent back and forth are an order of magnitude less with digital signature. So now it puts us in the realm of feasible. We can now solve this problem of consensus. We had this all-encompassing term of what can fail. Anything at all can go wrong. And with digital signatures, we have a viable process for a distributed system to reach consensus. So, and just a quick reminder, this whole time we've been talking closed permissioned networks only. Peer-to-peer networks is coming up. And in conclusion, the challenges of all these units working in parallel together, of changing a value from their initial value to a new value, meeting this definition when anything at all that can go wrong. The challenges are unscopable. Anything bad can happen. So to overcome this, we use a set of known protocols. Some of them are very simple. Some of them get complex. Cryptographic tools, digital signatures are extremely helpful. All these and combinations of these combined provide us a viable method to obtain distributed consensus in a closed and permissioned network.